Hello. In this video, I'm going to show how to solve this problem involving two blocks of wood, a block of wood and a block of metal. They're floating in water. The wood is less dense than the water. The metal is more dense than the water, and together they float. So we're told that the height of the wood is h. We're told that the volume of the metal is V. The area, the top is, or the area of the wood, cross-sectional area of the wood is A. We're trying to find, well, in the second part of the problem, we're going to be finding this height here. In the first part of the problem, we're going to draw free body diagrams. We're going to assume we know all three of the densities: wood, metal, and water. So let's start by drawing our free body diagrams. So we can draw our top diagram and our bottom diagram. We'll draw dots here to the side. That'll be my two objects. What are the forces? Let's start with the forces on the wood. We have gravity downward, M wood G. We have the tension downward from this rope that's connecting the wood and the metal. So we'll call that tension. And then going upward, we have buoyancy force, buoyancy. I'll call that force buoyancy 1. Now let's look at the forces downward. We have our forces on the metal. We have equal and opposite tension force upward. We also have a mass of the metal times G. And we also have a buoyancy force on the metal. The metal is also taking up volume, so it also produces a buoyancy force, buoyancy 2. Okay. So this would answer sort of this first question, which is to draw a free body diagram for each of the objects. But it's actually much easier to solve this problem as a single object. These two objects will, I guess, sink or swim together. I guess they literally sink or float together. So it's handy to draw them as a single object with forces on it. So let's imagine we have a single object. It has a gravity force downward of M metal plus M wood times G, and it has two buoyancy forces upward. Those are supposed to be straight upward. One is force buoyancy 1, force buoyancy 2. So that this free body diagram here for the entire object will be easier to analyze for finding the unknown height here than it would be to analyze both, because we don't have to deal with the extra tension forces. Okay, so now let's move on to part 2. Let's find the unknown height there. Okay, so basically what I'm going to do is I'm going to say the sum of forces in the vertical direction here, they need to balance out. The gravity force down needs to balance the buoyancy forces upward. So force buoyancy 1 plus force buoyancy 2 is equal to M metal plus M W times G. Okay, let's see here. What are each of these? So mass of the wood is going to be the density of the wood times its volume. So density wood times its volume, which is, well, its height, we've called H, and it has a cross-sectional area A. So AH is its volume, so that times rho wood would give you the mass of the wood. What is the mass of the metal? Well, this is just rho metal, the density of the metal times V. We're just told the volume is V. Okay, let's do the buoyancy force on the metal. That's rho water, V. Basically, the buoyancy force on something is the volume displaced. Well, in the case of the metal, all of the metal is underwater, so the volume of water displaced equals the volume of the metal times, and then we want to get the buoyancy force, so we multiply times rho of water and G, the gravitational constant. And here's the tricky one. We need to find the buoyancy force of the wood. So the important thing about the buoyancy force of the wood is that only the volume under the water, that volume there, counts the buoyancy force. So that buoyancy force is rho water times the volume, which is, let's write this, volume is area times h minus h above, where h above is the thing we're trying to find, times g. So rho times volume times g, where volume is area times the difference in heights, aka. So if this is h above, then this here is h minus h above. By the way, these water and above and metal and wood, these are all subscripts. They're just describing the variable. So it's a little hard to see in handwriting that that's a subscript, but it is. Okay, so now I have that whole equation. Let's write it out in detail. Rho water, area h minus h above, g plus rho water, Vg is equal to rho metal, Vg plus rho wood, AHG. You might notice that we can cancel our G's. Then after that, basically, we need to do algebra to solve for this. So let's first move this term to the other side. And actually, we'll put it, why don't we put it between the two? Now we'll move it over there. That'll work. And then what we'll do is we'll divide by this, by rho water A, because we want to solve for the h's there. Okay, so doing that, those two algebra steps in one, we get h minus h above is equal to, okay, so we'll do this term here, we get rho metal V over rho water A. Then we'll do the next term plus rho wood HA over rho water A minus rho water V over rho water A. Okay, and that allows us to cancel the two rho waters and cancel these two A's. Okay, and continue solving. We're going to move the H to the other side. So notice that these two terms each have a V over A in them. So I'm going to combine those. If I move this to the other side, it will have an H, as will this term here, so I can combine them, and I get minus A above is equal to, so I'm going to write this as V over A times rho metal over rho water minus 1. And then, so that the minus 1 comes from this term gives you that term. Then on the other one, we have plus H. So we're going to have two terms that have an H, this term and this term. H times rho wood over rho water minus 1. Okay, and then finally, H above is equal to V over A. I'm just going to switch these so I get a net negative sign. Rho metal, water, plus H 1 minus rho wood over rho water. Okay, and that is the answer. You can see most of it is just algebra there. Okay, we can do some interpretation of this. So rho metal, I would point out that rho metal is always greater than rho water. So this term is negative. This whole thing here is negative. That represents the fact that the metal is going to reduce H above. This term here is positive because rho water is less, or rho wood is less than rho water. So this is how much it floats above. This is how much it's being dragged down by metal. If the whole contraption is to float, then this term here better be more positive than this term here is negative. Otherwise, well, it sinks. What else can you tell? Suppose, suppose rho metal is equal to, suppose we didn't have metal. Suppose V was 0, so we didn't have any metal. Basically, what this would tell us, that the height here is 1 minus rho wood over rho water. As rho wood approaches rho water, the H above goes to 0. Basically, as wood becomes the same density as water, it just barely floats at all, or it just becomes basically just water. So that sort of makes sense. So that is how you solve that problem.